Now, when we look at the signal as to why exactly do we have certain portions of the signal that is large and certain portions that is small, remember that what this signal is made up of, for all intents and purposes, this contains the carrier frequency, right? So we'll just call that FC, that's the carrier frequency. And it contains two sidebands. We have the portion where the carrier and the intelligence, I'll call that's our voice signal, have, you got the difference between them, and then we got the addition of them, okay? This would be equal to your lower sideband. This would be equal to your upper sideband, okay? So that's what's created when we go through this process, okay? So we have this combination. Now, at this point, we have three frequencies. So for all intents and purposes, we have hidden the intelligence in this amplitude modulated signal now. We've hidden it. For all intents and purposes, the intelligence is no longer there. If you were to grab a spectrum analyzer and look at this, you will not find the intelligence in here. You will only find the carrier frequency, the lower sideband, and the upper sideband. It's up to the receiver to extract and demodulate this to retrieve the intelligence, which is why it's important to get the modulation just right, because then we can extract the most accurate signal that we can. Okay, and we'll talk about that in a little bit. Okay, so going from that, we're left with this kind of waveform right here. Now, what we're going to notice about this guy, there's some key things to notice. We have points where the upper sideband and lower sideband are in phase at this point here, with the upper sideband and lower sideband are in phase with the carrier, and we got points where it's going to be out of phase with the carrier. Okay, so when it's out of phase with the carrier, that becomes the difference. You can see here we got portions where the lower sideband and the upper sideband are approximately 45 degrees out of phase. Well, if you have something that if you compare the amplitude of something and something that's 45 degrees out, it's going to be the resultant. Remember when we get into phasors and the resultant vector, if you have say a 90 and a 90, the resultant vector is 45. Okay? So that becomes the difference between them. And that's what's happening all throughout here. So there's points where they're in phase. When they're in phase, the vectors add, right? Their amplitudes add. When they're out of phase, they kind of become the difference. Okay, you can see where approximately the phase angles are so you can see this phase angle is rotating this way, this one's rotating this way, then they pass, right? So this one has gone across. Now its phase angle is changing this way, this one's change angle is phasing that way. Then we got at this point approximately 90 degrees out of phase, right? At this point here. And then we get to the most crucial point, which is right here, which is completely out of phase. Okay, sorry, this is, so at this point here, we're completely out of phase by 180 degrees, completely backwards. 90 degrees out, 180 degrees out. Okay, and then the rotation just continues as such. So as far as, now when we talk about power, it's important to note that the power difference between the carrier frequency and the upper and lower sidebands is approximately going to have a quarter of the power. Okay? So a quarter of the power of the carrier frequency. Okay? Which is also happens to be 6 dB. Right? Remember when we talk about bandwidth, now there's this relationship to consider when we talk about the quality, right? Which is going to be the Q of the sine wave or the bandwidth, right? And it would be with the resonant frequency over bandwidth, right? And we have this inverse relationship that happens between Q, right? So if the quality of the circuit goes up, the bandwidth goes down. Now in receivers, it just so happens that we want very selective receivers. Okay, so we're aiming for a more narrow bandwidth because we don't want to reach everything that we don't want to pick up everything possible. But what we do have to consider when we are trying to pick something up through, say, a low-pass filter or a high-pass filter or a band-pass filter, we need to make sure that we include the frequencies that the upper and lower sidebands are at. Okay, because if we don't, we'll end up clipping them and we'll lose some of our intelligence, because you can imagine that if the whole package here, this is why we call it the envelope, if this whole envelope contains the intelligence, we need the whole thing in order to extract what we need. Okay, so again, the carrier frequency, the upper and lower sidebands are approximately 1/4 the power of the carrier frequency. Upper and, let's say, lower sidebands, right, which just so happens to be 6 dB down. Okay, and remember when we were talking about the cutoff frequencies for the bandwidth, the cutoff frequencies are 3 dB down. Okay, so that brings us to why it's shaped the way it is. So we'll go into figuring out how to calculate modulation. So we have the shape of the thing. Now for calculating, if I wanted to figure out what the modulation is, if I knew what the potential of the intelligence is and the potential of the the carrier, I can just divide those 2 times 100, and that's going to be the percent modulation. If I don't know that, and all I know is the wave, I can measure the peak points, okay, and I can measure the maximum peaks and the minimum peaks. Okay, that's what these Vmax and Vmin mean. So we're going to measure the point where it's max, subtract it by the min, then we're going to add them and multiply that by 100, and now we got the percent modulation. So in this example, say this was from here to here was, say, 10 volts peak, okay? And then we had, say, 5 from here to here, 5 volts. I'm going to keep this simple just for explanation purposes. So the first part of this, I'm going to subtract 10 by 5, so we're left with 5, right? And then I am going to divide by the sum of them, which is 15, right? And then divide that, multiply that by 100, right? And then you get